Hi, this is Alex from devstories.eu, Python, Cheminformatics, and AI, Episode 3 of 22. To a computer, a molecule is not a physical object taking up space. It is strictly a graph of nodes and edges waiting to be parsed. If you cannot efficiently navigate that underlying graph, you cannot analyze the chemical structure. This brings us directly to molecular graph traversal. In RDKit, a molecule object acts as a primary container for this graph data structure. To inspect the nodes, you use the getAtoms method. This returns an iterable sequence containing all the atom objects in the molecule. You can write a simple loop to step through the sequence one by one. For a concrete scenario, suppose you need to extract the atomic numbers of all your nodes. Inside your loop, you can call the getIndex method to find the unique numerical identifier for the current atom, and the getAtomicNum method to find out exactly which chemical element it is. By iterating through, you process every node systematically. Nodes alone do not define the chemistry. You also need the edges connecting them, which you access using the getBonds method. Just like with atoms, this provides an iterable sequence of bond objects. A bond knows its exact place in the graph. By calling the getBeginAtomIndex and getEndAtomIndex methods on a bond object, you extract the specific numerical identifiers of the two atoms it connects. You can also read the bond type, determining if it is a single, double, or aromatic connection. Here is the key insight. RDKit treats bonds as first-class objects in the graph hierarchy, meaning you query them independently rather than digging them out of atom properties. Navigating individual nodes and edges is standard graph logic, but chemical graphs frequently feature cycles, better known as rings. You do not need to write your own cycle-finding traversal algorithms. RDKit pre-calculates these cycles when the molecule is instantiated. You access this data via the getRingInfo method. This returns a dedicated ring information object rather than a simple list. When you need deeper structural details, you can ask this same object for the atom rings property. This gives you a collection of sequences, where each sequence contains the exact atom indices that make up one specific ring in the graph. You could even pass an atom index to the ring info object to ask if that specific node participates in a ring of a particular size, such as a 5 or 6-membered cycle. Traversing a molecule is ultimately chaining these basic operations. You grab the ring info to check the macro structure, you loop over atoms to read node-level data like atomic numbers, and you loop over bonds to map the specific edge connections. Once you stop seeing a molecule as a physical entity and start seeing it as a predictable collection of indexed nodes, edges, and pre-calculated cycles, extracting structural properties becomes a standard data parsing task. That's all for this one. Thanks for listening, and keep building.